Runge phenomenon, equidistant versus Chebyshev nodes. We will contrast equidistant nodes with Chebyshev Gauss nodes and examine how node placement governs stability. The Weierstrass approximation theorem states, for every continuous function on a closed interval and for every tolerance epsilon greater than 0, there exists a polynomial p such that the sup norm of f minus p is less than epsilon. This ensures uniform approximation, but it does not address interpolation at specific nodes, nor the stability of that process. Interpolation is made explicit by the Lagrange formula. P sub n of x equals the sum over I of f of xi times L sub I of x. Each basis function, L sub I, equals 1 at its own node and vanishes at the others. Consequently, P sub n is the unique polynomial of degree at most n that matches all data points. The central question is how the choice of nodes influences the quality of this interpolation.
We will test interpolation on equidistant nodes over the interval -1 to 1. We will raise the interpolant's degree to a moderate value and see how well this works. First, sine of 5x. Even with moderate degree, the interpolant tracks the oscillations closely. Across the interval, the fit looks reliable. Next, log of 1 plus x squared. The function is smooth on the interval, and the interpolant hugs the graph almost everywhere. Nothing alarming appears. The method seems robust. Finally, e to the x squared. Despite the growth away from 0, the interpolant remains accurate on this range. For these examples, equidistant nodes seem perfectly adequate.
If polynomials approximate every continuous function uniformly, should interpolation on equidistant nodes improve with degree? No, uniform approximation is an existence result. Interpolation stability depends on node placement.
Here is Runge's function. F of x equals 1 over 1 plus 25x squared, interpolated on equidistant nodes over the interval -1 to 1. We will raise the degree. At 10 nodes, the interior is reasonable, but the endpoints overshoot. Maybe using more points will help. With 50 equidistant nodes, the endpoint oscillations grow rather than decay. The maximum error increases. It actually got worse. But why?
Equidistant nodes, error-bound and exponential instability. Define lambda sub n of x as the sum of the absolute values of the Lagrange basis, L sub j of x. Its sup norm is lambda sub n. The interpolation error satisfies the Lebesgue operator bound. The sup norm of f minus I sub n f is at most 1 plus lambda sub n times the best degree n approximation error. On equidistant nodes on the interval -1 to 1, lambda sub n grows exponentially with n. Endpoint oscillations and amplification follow. This is the Runge effect. For f of x equal to 1 over 1 plus 25x squared on -1 to 1, the sup norm of f minus p sub n diverges when the nodes are equidistant. So, how can we fix this? Let us go back to our graph. Keep all equidistant nodes fixed and allow one interior node to move between its neighbors. Zoom in on that pair of nodes. As the node moves toward its neighbor, the local oscillation collapses around the cluster. Shift it the other way and the reduction follows. The error contracts where the nodes clump. Interesting how clustering nodes reduces the error locally. Return the node and the oscillation reappears. Local clustering helps. The geometry of the nodes is the lever.
Chebyshev nodes do exactly this. They cluster near the endpoints. Chebyshev Gauss nodes on the interval -1 to 1. Construction. Place equally spaced angles on the upper semicircle, then project vertically to the x-axis. Marquee angles on the arc. Drop each point straight down to the diameter. The vertical projections land on the x-axis. These projected x positions are the nodes. Formally, x sub k equals cosine of open parentheses 2k plus 1 over 2 times n plus 2 close parentheses times pi for k from 0 to n. Notice the increased density near plus and minus 1. The spacing tightens toward the edges.
Chebyshev nodes, small Lebesgue constant and stability. Define lambda sub n of x as the sum of the absolute values of the Lagrange basis L sub j of x. Its sup norm is lambda sub n. The interpolation error satisfies the Lebesgue bound. The sup norm of f minus p sub n is at most 1 plus lambda sub n times the best degree n approximation error. On Chebyshev Gauss nodes on the interval -1 to 1, lambda sub n grows like 2 over pi times log n up to a constant. The endpoint behavior remains controlled, and the operator is uniformly stable. Asymptotically optimal, Faber's lower bound shows lambda sub n is at least c times log n for any node set, and Chebyshev achieves order log n. Let's use Chebyshev nodes on our graph. Switching to Chebyshev Gauss nodes. As the nodes migrate toward plus and minus 1, spacing tightens near the endpoints and the boundary ringing subsides. Notice how Chebyshev nodes naturally cluster near the edges. Hold the Chebyshev layout and now vary the degree. As n increases, the interpolant operator remains well conditioned. The Lebesgue constant grows on the order of log n, so endpoint oscillations do not amplify. With Chebyshev nodes, the interpolant stabilizes and converges as n increases. Conclusion. 1. Equidistant nodes can amplify error near the endpoints, the Runge effect. 2. The root cause is the Lebesgue constant. Lambda sub n grows exponentially for equidistant grids. 3. Chebyshev Gauss nodes cluster near plus and minus 1 and keep lambda sub n small, approximately 2 over pi times log n. Side-by-side comparison at the same degree. On the left, equidistant nodes produce an interpolant with endpoint oscillations. On the right, Chebyshev Gauss nodes yield a stable curve near the boundaries while matching the samples. Takeaway: for global polynomial interpolation on -1 to 1, use Chebyshev nodes or use splines.
If this helped, subscribe for the follow-up on cubic splines.